Hello everyone, welcome back to section 8.5. This is where we're going to look at the acids and the bases and how they react with each other, because we talked about before that they're the opposite of each other. That is, one it goes from 7 to 0, the other, that base, goes from 7 to 14, and so they're the opposite. And so as one goes up, one goes down. We've talked about that. We've also looked at pH and what that means, and we've also looked at the hydronium ion concentrations and the hydroxide ion concentrations. So now we're going to look and see what happens when we combine those together in a reaction. Acids react with metals. So metals, remember, are on the left side of that zigzag line, and so they're going to be your potassium, sodium, aluminum, zinc, tin, things like that. When you react an acid with a metal, you are going to produce hydrogen gas. That's a rule. Okay? So if I add hydrochloric acid to potassium, and that's metallic potassium, I'm going to get potassium chloride, which is a salt, and hydrogen gas. Forever and ever, amen. That's what's going to happen when I am going to react an acid with a metal. Okay? I'm going to produce a salt, and I'm going to produce gas, hydrogen gas. So what this is asking you to do is to write a balanced equation for magnesium metal with hydrochloric acid. And remember, when it's just magnesium metal, it's just magnesium, Mg with an S, because it's a solid. Okay, and so you're going to have magnesium plus hydrochloric acid, and what did I say? You're going to always produce a salt and an acid. A salt and a gas, right? So go ahead and try that. Look back at the other slide if you need to. Okay, so how did you do? It's basically the same as potassium. Sodium would be the same. The only thing that changes is what the salt is, because the salt is made from whatever metal you started with, and you're always going to produce that hydrogen gas. Notice that I had to balance this because magnesium chloride, since magnesium is a +2, I know this is from a long time ago, and chloride is a -1, you have to have 2 of those. So that's how we get the MgCl2. And then to balance the equation, we had to put a 2 in front of this because we had H2. That's how hydrogen gas exists in nature. I know, you thought you were done with that. You've got to go back and remember that stuff again. When acids react with carbonates or hydrogen carbonates, they are also going to produce a gas, but this time, instead of hydrogen gas, they're going to produce carbon dioxide. And that makes sense if you look at this reaction, because a carbonate has a C's and O's in it, right? So you've got carbonate and you've got an acid, and you're going to produce carbon dioxide, and again a salt and water. So if you've got hydrochloric acid with calcium carbonate, you're going to end up with CO2. You're going to have the salt, and so when you make the salt, you're going to have whatever was attached to the carbonate, and it's going to combine with the negative chloride, right? And so that's going to make your salt, in this particular case, calcium chloride, and then you're also going to produce water. In the case of sodium bicarbonate, okay, because that's the bicarbonate, you're still going to produce carbon dioxide. You're going to produce your salt with your sodium and your chloride, and you're going to have water. Notice it's liquid water, so that just means that you do actually produce water, and it'll be salty, won't it? Okay, so here's magnesium carbonate and hydrochloric acid. Hydrobromic acid, and you need to write and balance that equation. What are they going to produce? They're going to produce carbon dioxide, the salt, and what else? Water. That's right. Okay, so try to do these. How'd you do? Okay, I hope you didn't forget to balance, because you may have forgotten that, this whole thing about the +2, because magnesium is in group 2 and -1 for bromine. Putting these together, you might have to go back and practice that a little bit, okay? But I'm sure you'll do fine. All right. So in a neutralization reaction, that's when you're going to add an acid and a base together. Okay, so let's just review for a second. All right, so with acids and metals, when an acid, such as hydrochloric acid, reacts with a group 1 or 2 metal, then we're going to produce hydrogen gas and the salt. When we react a carbonate or a bicarbonate with an acid, we're going to produce carbon dioxide, the salt, and water. When we neutralize, that is, we just add the acid and the base. Remember, they're opposites, so they're going to try to cancel each other out, basically. You're going to have the acid plus the base, and you're going to produce a salt again, okay, and water. That's it. So basically what happens is that the sodium will attach to the chloride, in this case, and the H grabs the OH, and so HOH is the same as what? Water. So it's just the salt and the water. So these are pretty easy. So if it's a strong acid, okay, and by the way, that is basically the molecular form of this reaction, okay, the molecular equation of this reaction, that when you have the molecules written like this. In neutralization, if we write a strong acid and a strong base as their ions, we can see how the hydrogen ion and the chloride ion, the positive and negative cation, anion, and the cation and anion of the base produce these ions. But remember that when we neutralize, this is liquid water, so it does not have ions in it. Okay, it's the molecule of water. So when you're looking at this reaction, notice that some of the things on the left side of the reaction, that is the reactants, is the same as what's on the right side. So if we look at these and we mark out what's on the left and the right side of that arrow, we see the sodium and the chloride ions are there. So basically they're just hanging out throughout the whole thing. What we see is really what's reacting is the hydrogen ion, the hydroxide ion, and they're making the water. And so the overall reaction is H plus, or hydronium, plus OH minus gives us water. So if you look at it that way, basically these are the net ionic materials. Net as in, that's the total ionic. This is the net ionic. That's what's really going on as far as the reaction goes. So when we are going to put these things together, we're going to write the reactants and the products together. We're going to balance the hydrogens in the acid with the OHs in the base. We're going to balance the water with the H plus and the OH, and then we're going to write the salt from what's left. Okay? So if you've got magnesium hydroxide and nitric acid, you're going to balance the H's with the OHs. Okay, so you've got 2 H's, and so you're going to need 2 H's here. Alright, then you're going to say, okay, then I'm going to balance the waters with the H's and the OHs. So I've got 2 H's here, 2 H's there, so I'm going to need 4 H's, so 2 times 2 is 4, and then that should balance the oxygens as well. And then what salt I'm going to have is going to be with the magnesium and the nitrate, okay, because this is a plus and this is a minus, so you're going to have the plus and the minus go together. That's the only thing you got left. So select the correct group of coefficients for each of the following. So just all you're going to do is balance these. And it's going to take you through the steps, okay? Just like we did, like we showed you in the little stepwise model. And you're going to end up with 3 hydrochloric acids, 1 aluminum hydroxide, 1 aluminum chloride, and 3 waters. With the barium hydroxide and the phosphoric acid, you're going to end up with 3 barium hydroxides, 2 phosphorics, 1 barium phosphate, and 6 waters. Basic compounds in antacids, antacids, some have calcium, some have magnesium, and Alka-Seltzer actually has potassium and sodium in it. And so these are all group 1A or 2A metals, except for aluminum, with your hydroxides. So let's write the neutralization reaction for stomach acid, which is hydrochloric acid, with the ingredients from Mylanta. So just do them separately, okay? So do HCl plus aluminum hydroxide, and what you're going to get there, and then HCl with mag hydroxide. Make sure you do your balancing, okay, because you're going to balance your H's and your OH's, right, as you go across. Because you're going to have 3 H's if you got 3 hydroxides. You're going to have 2 of those if you have the mag. Alright, you're going to have water. And then the aluminum and the chlorine. Remember, that's a plus 3. You know that because hydroxide is a -1 and it takes 3 to make a compound with that. So AlCl3 and MgCl2. Alright, and then you've got 3 chlorines. You've got, okay, so we've got to balance the hydrogens. You've got 3 hydrogens here and 3 hydrogens there. So you're going to have 6. So it's going to take 3 of those, alright, and then that should balance everything out. Alright, and then got that a little close together, didn't I? So mag chloride, you've got 2 and 2, so that's 4, so it should be, plus 2 waters. Let's see how we did. Yep, I believe we did it. Okay, so one of the most common ways to do an acid-base reaction is to do something called a titration. And in a titration, you can determine the molarity of one component that you put in the flask here if you know the molarity of the titrant. In this case, they've got a base as a titrant in the burette, and they've got the acid solution in the flask. You use an indicator when you do a titration, and we mentioned this one a little bit earlier. It's called phenolphthalein. It's a very long word. And it turns pink. When it's neutral, it's clear. And when the solution is basic, it turns pink. And so that's how we know that our pH is being neutralized, is this color. I don't know how well you can see it there, but it's get a little bit pink in there. And when you reach the end point, you will see it just turn pink there, and it will stay. It won't go away. When you reach that point, then you are going to measure how much base it's taken to reach that end point, that neutralization point, and it's going to allow you to calculate, if you know the molarity or concentration of the base, then you're going to be able to calculate the molarity of the acid. Okay, so you're going to state what you need, write your plan, state your equalities and conversion factors, and then set up the problem to calculate. So if the problem here is, what is the molarity? So this is the one we're looking for. What is the molarity of a solution if 18.5 milliliters of a 0.225 molar sodium hydroxide are going to neutralize 10 milliliters of this unknown acid? And so it's a standard neutralization reaction. So we've got 18.5 milliliters of a 0.225 molar sodium hydroxide. We've got 10 milliliters of HCl, and we don't know what that molarity is. So that is what we're going to try to figure out. So what you're going to do, remember, we're going to go back to stoichiometry. I heard you groan all the way through my headphones. Okay, 18.5 milliliters. You're going to convert that to liters. Why? Because molarity is in moles per liter. You're going to convert that to moles of the sodium hydroxide. You're going to use your coefficients of how the HCl and the sodium hydroxide react to go from sorry about that, I had a phone call. Okay, so you're going to write the plan to calculate the molarity or the volume. So you got 18.5 milliliters here, as I said. Going to convert that to liters because your molarity is moles over liters. So our coefficients, remember, take us from moles of sodium hydroxide to moles of hydrochloric acid, and then that allows us to calculate the liters of the hydrochloric acid. So what you're going to do is, you've got those inequalities like we've learned about and when we were doing stoichiometry, and you can go back to that chapter if you need to refresh yourself on those. But we know that because of the way this is, that it's a 1-to-1 this time, 1 hydrochloric to 1 sodium hydroxide. We've got 0.225 moles per 1 liter of sodium hydroxide, because that's what M is equal to, right? Okay, so 0.225 moles of sodium hydroxide per 1 liter of sodium hydroxide. I know this is my molar ratio. Where did that come from? Came from this. Okay, the molar ratio of hydrochloric and sodium hydroxide. And remember that these can be flipped or they can be the same. It doesn't matter because they're equalities. So now I have 18.5 milliliters of 0.225 molar sodium hydroxide. So I've got to convert milliliters to liters, and I do that by saying that there's 1,000 milliliters in 1 liter. Then I have 0.225 moles per liter of sodium hydroxide times the molar ratio, 1 mole of hydrochloric per 1 mole of sodium hydroxide. If I multiply everything on the top and then divide by everything on the bottom, I get 0.00416 moles of hydrochloric acid. And so to get the molarity of that, I know that this is how many moles of hydrochloric acid I have in 10 milliliters. Okay, and 10 milliliters, if I convert that to liters, is 0.01 liters. So 0.00416 moles of hydrochloric in 10 milliliters, or 0.01 liters of hydrochloric, gives me 0.416 moles per liter, remember, of hydrochloric. Okay, so let's calculate this one, and I'm gonna go through the steps with you, writing this on my pad. maybe, if I can do it. Okay, so they want me to calculate milliliters, okay, so that's what I'm going to be looking for, of 2 molar sulfuric acid. How much is required to neutralize 50 milliliters of 1 molar KOH? Alright, so I'm looking for milliliters. So what do I start with? Well, I start with the volume I know, and they've already given me the balanced equation, so I don't have to do that. Alright, this time I'm going to have a 1 to 2 ratio. Alright, so I've got to watch that. So I start with 50 milliliters of KOH. Alright, and I want to get that to liters because my molarity is moles per liter, not moles per 1,000 or moles per milliliter. So there's in 1 liter of KOH, there's 1,000 milliliters. That allows me to cancel my milliliters. Okay. I know the molarity of KOH is 1 mole of KOH. Where's that come from? Because molarity equals moles over liters. Okay, you got to remember that. 1 liter KOH. Okay, so I can cancel that. Alright, so I'm at moles of KOH. How do I get from moles of KOH to moles of sulfuric? I use the what? Molar ratio. I know moles of KOH has got to go down here, so I can cancel. And so for every 1 mole of wait, sorry, I almost messed up. For every 2 moles of KOH, there's 1 mole of sulfuric. Okay, and so that cancels the moles of KOH. And then times what? Well, I tell you what we'll do. We will say what is that equal to first. Alright, so 50 divided by 1,000 divided by 2. Y'all doing this with me, I hope. $50 times 1 times 1 times 1 divided by 1,000 divided by 2 is, I get 0.025, and let's see, where am I? Moles, sorry about the handwriting, of H2SO4, and then how many milliliters? Oh, that's what I'm looking for, isn't it? Okay, so I've got moles, so that's how many moles. I know the molarity. This time I know that I've got 0.025 moles, and that's going to be divided by some liters. It's going to equal 2 moles per liter, right? So how am I going to do this? Okay, I'm back. Alright, so we get the moles of sulfuric acid. Okay, so that's what we have right here. That's what we just calculated. And then, so 0.025 moles of H2SO4 times, I know the molarity, but now moles is going to have to go down here. So I know that I've got 2 moles per liter of H2SO4. Moles will have to go on the bottom. Why? Because it's got to cancel this. So I've got 2 moles per 1 liter and times 0.025 moles. Alright, so that equals 0.0125 liters. And so if I want to know how many milliliters that is, then I can multiply it by 1,000 milliliters per liter, or I can just move the decimal place 3 places. Either way, I'm going to get 12.5 milliliters, which should be A if we did it right. So let's see. We're going to watch them go through all their steps. And if this helps you, use this. Canceling out, and yes, they got 12.5 milliliters, which is what we got. And that's the end of 8.5. I hope you enjoyed it. We only have one more section left of this chapter, and that will be section 8.6.